Hello, you little demon dwellers. We are back in action in our forces and Newton's Law chapter. So we've covered forces, free body diagrams, how to draw them, and hopefully by now you understand Newton's first law and how important that is in things like seat belts and a lot of real life applications. We are now going to apply some calculations using Newton's second law of motion. So if we look at what Newton's first law is about, that describes when there's no net force. Things will keep doing what they're doing. A ball will keep rolling. An object, a body in a car will keep flying even afterwards if there's no seatbelt. Newton's second law, however, is when there is a net force, so things are unbalanced. And we've already learned about this a little bit, but we know when there's a net force on an object or the tug of war isn't equal, that will make the object speed up and accelerate in the direction of the net force. So what Newton's second law really says is that the net force is directly proportional to how heavy an object is and how much it's accelerating. So this is super important, and as the net force gets bigger, the acceleration will increase, which makes sense. If I push a shopping cart harder, it will go faster. This is also important for us to think about mass. We know that if we have a ping pong ball versus a bowling ball, we'll look at an example in a second here, they will accelerate at different rates because of their mass. Usually we'll write Newton's second law as net force equals m times a, and remember, the net force is when we add all of them up. It's not just one force, it's what the net overall combination of all those. And then we'll use m times mass and a times acceleration. Just a little concept idea here. So let's apply Newton's second law in a real world situation. We know the net force depends on mass and acceleration. If we have a ping pong ball and a bowling ball and we push them both with the same net force, we know that the ping pong ball is going to accelerate much more because it has a tiny mass. On the flip side, a bowling ball has a much higher mass, therefore it will not accelerate as fast. That's the kind of idea that you have to think about with these things. Even if they have the same force, they're going to accelerate differently because of their mass. Think about those relationships as you're doing these problems here. We're going to do one sample problem together, and then you guys will be able to do assignment number 3 on your own and see how we do the steps. An example, Newton's second law would say, what net force would be required to make a 12 kilogram shopping cart accelerate at 2 meters per second per second? So just like we've been doing the whole time, we write the blank equation, we plug it in, and then we solve. So we know, since we're looking for net force here, this is Newton's second law. So the net force equals mass times acceleration. There's my blank equation. Now I'm going to go plug stuff in. The mass of the shopping cart is 12 kilograms. We know we're going to make that shopping cart speed up at 2 meters per second per second. That's its acceleration. So if I go solve now, so blank equation, plug it in, and now I solve, my third step, that's going to be 24, and then these units are going to look kind of crazy, but it's a kilogram meter per second squared, and we know that that actually is a Newton. So the net force acting on that shopping cart would be 24 newtons to make it speed up that much if it weighs that much. And technically, since it's accelerating in the positive direction, we could also say the net force is 24 newtons to the right. Just remember, you're going to start with the blank equation, you're going to plug it in, and you're going to make sure you pay attention to your units. All of today's problems will ask you to solve for the net force. The net force equals mass times acceleration. That's what Newton's second law is all about. Go get after those practice problems.